So once again, thank you very much and welcome to Sam from 7200, Team 7200 Banting Memorial.
Hi everybody. It's great to be here. I'm pretty excited to talk to you all about something that I really like. I really enjoy. Looking at FRC just as a kind of widespread, huge thing. It's a little overwhelming to just look at, but after you start getting involved, you realize that it's all just a learning curve, and you pick up on it pretty quick when you enjoy what you're doing. So looking at something when you first become a part of it is pretty difficult to grasp, but you catch on very, very quickly. Um, you are going to be involved with a lot of people that are going to be very helpful in helping you learn this stuff. And instead of kind of putting you out there to learn it yourself, they're very hands-on about what's happening and what's going to happen because of what you're doing. So everything that you're going to be exposed to is going to be pretty gradual. And they're not trying to throw you in there and really confuse you. Everything is very well managed. Um, During competition times, the build season can get a little bit hectic. It gets very busy very quickly, but as long as you enjoy what you're doing and you slowly start to understand what you're doing, or you already have a bit of knowledge towards what you're doing, it's enjoyable, and you're working around a bunch of people that have very similar interests to you, and you meet a lot of really good people in the process that are from all over the world, and in places that you would never really think to meet people. If you give me a second, I'll share my screen. I have some pictures of electronics here. I'm sorry, just give me one second. Okay, now that everybody can see what's happening here. Can everybody see this part of the screen?
Yeah.
Okay, so this is the most recent robot that we're working on right now. You can kind of see some of the major parts just is mounted on top. So for instance, this is the battery that powers the whole part. You've got a lot of wires coming out of one bit, each going to wheels. I'm just kind of gonna explain some of the bigger portions and leave the rest for you to figure out on your own. These big orange lights are in every robot that goes to competition, and it's just there for safety to tell people when the robot is on, when it's enabled, when it's disabled, when it's going to do things. It's just a kind of it's something to just show when you should take a bit of caution around the robots, because at times, if things are done incorrectly, or even if nothing's wrong, they do tend to do some kind of random things at times. The battery plugs into this part right here, which is just a distribution center. So you can plug in all kinds of fuses here to protect the electronics that you are plugging in. And then you just plug it in power and a ground wire, and you can send that wherever you want. So, for instance, we have it being sent out into some pieces that are sent to the wheels, and it kind of powers the entire robot, technically. And right down here is just the on and off switch. It's just kind of a breaker. You push in this little tab to turn it on, and to shut it off, you just push this big red button. The tab will flip out, and the robot will shut off. There are little modules like this as well. This one specifically is for pneumatics, so air-based cylinders products. But it also has some settings for a CAN bus, it's called, that goes to the motor controllers here. And the motor controllers are basically just taking input from wherever you ask it to and changing what's happening on the other end. So you send power from the distribution into one end, and from there, you plug the power into the motor on the other side. You plug in something that will give it values, inputs, whatever, and change what this does to the wheel. So we'll change the speeds of the wheel, how fast it wants to move, what the max it can move is. It really just regulates everything that happens to the motor. Whereas when you just plug the motor into the power, it's just going to go full speed forever. It doesn't change. CAN bus is kind of like the main bus for all of the code. So the code will kind of go through this wire in a big link, and different pieces will pick up the information that is for them, that they want, that is assigned to them, and use it as an input that will change something outside. In the middle here, we've got a gyro. These will check for angle, for rotation, anything you tell it to do. On this specific robot, it's called field centric, which means you tell it which side of the field is forwards. No matter which way it's turned, that will always be forwards. So this will take the forwards as 0. And if you turn the robot to any degree, it'll just remind the robot that forwards is at a new degree and no longer 0. Up here underneath this wire, this is the radio. So it actually shows up on a computer as a Wi-Fi network. And you connect through the Wi-Fi to it, and then using a FRC Robotics program, you can enable, disable, and connect controllers to your robot through that. It makes it really easy to connect to it. You learn really quick. It's just like connecting to a Wi-Fi network on your phone or your computer, except instead of getting a connection that will like access the internet, it's strictly just controlling whatever it's plugged into. Up here is probably one of the most important parts. This is called a RoboRio, and it is basically the brain for the entire robot. So everything, or almost everything, that is on the robot will be connected to this. And this just takes a whole ton of different code and divvies it between every part, telling it what to do, when to do it, why it's doing that, and ultimately controls everything that's happening around you. This type of robot is very special. It's one of the first ones we have. Usually the drive system that we had before were called tank drive, which is there's a row of wheels here, a row of wheels here, and it can go forward or backwards, or it can spin on the spot. These wheels on the other end have 2 motors per corner. One of them is to drive the wheel. One of them actually will rotate the entire wheel. So you can have it facing one way and moving a totally different direction. Looking closer here, this is just a closer look at one of the power distribution modules. This one is a bit older, but they all kind of work the same. You take fuses that just protect whatever's plugged into them. So instead of blowing up a part or breaking something, it'll blow this fuse and just disconnect the power from that part. It saves all the expensive bits, and these cost close to nothing. If you look over here, you can see where the CAN bus connection are. Usually they're green and yellow wires. Almost always you see them as green and yellow wires, where one of which is the ground and one of which is the signal. You can see where the battery input comes in here. So it's just a ground input and a power input from the battery. And all of these will have that same output. uh, which can also change depending on the fuse you put in them. And then you can kind of just send off all of these power wires to different pieces. This is usually close to the middle of the robot because you want to keep everything very managed. You want to make sure when you're looking at something, it's not a huge bird's nest of wires and cables, and it's kind of confusing to look at. You want everything to be very organized and easy to pick apart. So everything's color coded, everything's routed, everything going to one part are usually very close together and separated from other parts. And looking here, it's just a closer look at one of the most common motor controllers that you'll see in the field. These are the ones that we use. For the swerve drive robots, the ones that are a little bit more complicated, they use some more expensive parts. They use some different pieces that just have some extra options. But these are your basic output. You can go online and find a million different files, folders about these motor controllers. And the main premise, you have power that goes in from the battery, from the power distribution. So just a power wire and a ground wire. And on the other side, you have an output, which is the same power and the same ground. And right here on the side is 3 wires that are telling the motor controller what to do. So you've got a ground, you've got a power, and you've got a signal. The ground and power just give this the necessary voltage to do anything. And the signal is what's actually telling it to do whatever it's doing. So what would happen is these wires on the top here would be plugged into a motor. And what these wires do is change the voltage that's being allowed through it to change the speed, the time, whatever's happening with the wheel. And it's instead of just having something on indefinitely forever, it's running something based on what you're giving it. So you give it inputs from a controller, from a computer, from whatever, and it will take that information and use it to do something to the motor. I've just got a picture here from one of our past projects. We built a robot goalie, the one that was at Georgian. And it's just kind of a look at what happens when you finish everything. I don't have a picture of the back here, but it is a tank drive robot. There's just 2 rows of wheels, one here, one at the back there. So it moves left and right. Both arms are connected to some pneumatic pistons. So you push a button and it will shoot this arm up. It will flick this hand up. And if you look kind of on the side here, you can see this blue piece and this red piece. Those were actually the kickers, which are 2 more pistons, and they would kind of flip out to the side and block what was going down low. But if you Google a robot hockey goalie on YouTube, on whatever, this is what you're going to see, because it's the only one that that's really made it anywhere specifically, and it's built by a bunch of high school students. So it shows that if you're interested in something, if you want to do something, if you think something's cool or whatever, it's very easy to catch on to it because you're always going to be paying attention, because you're just always wanting to learn more about what you're doing. Overall, though, it looks complicated, but it really is not. The more complicated bit from the base is building on top of the robot. So building up based on what competition you're doing, what the event is. But working with a big group of people, it's a lot of ideas being thrown out. You kind of pick bits and pieces from all of them, and you can really, really build something you wouldn't have thought of yourself. It's a lot of teamwork. It's a great skill to have. It's a lot of effort. There's a lot of time that is invested. But overall, after you have a finished project, you're looking at it and you just see what you've completed, what you've accomplished. There is a lot of fulfillment looking at something that exists only because you've thought of it, and that wouldn't have existed if you didn't work with those kind of people in these kind of conditions. I just see a question here in the chat. How to make sure CAN wire or other wires can be connected secure. Our robot always has loose connection or issue on field. So for our power distribution modules, some of them are screws. So you actually unscrew it and it lifts a tab. You really tighten the screw down and it'll kind of squish the wires closed, really press it. On other kinds of connectors, it's just a switch. You flick it up and it lifts the thing up. Stick a wire as far in as you can. I like to always make sure that it's really stripped. If you don't strip enough off the end, when you shove it in there, you might actually be clamping down on the rubber insulator, not the actual wire. But you just kind of clip it down, make sure it's in there, give it a couple pulls. It's always good practice to get other people to fact check your work, look at it as well, make sure it's plugged in the right places, everything's secure. Honestly, it's just a lot of kind of trial and error, a lot of checking and making sure something's reliable. I don't see you using a VRM voltage regulator module. This robot is not really competition ready yet. We're kind of just looking at it as a widespread thing. So we kind of went into this year with the goal of having one of these before the competition. This was like the first prototype we have. It's very bare bones. We're still editing everything, but this is kind of the minimum that you need to run it. If you do look in here, you can't see there's one of them, but this is strictly for the radio. That's just because we've had First has had kind of problems with these radios in the past where you get a good shove or a push or bump on the field and you'll disconnect from the robot temporarily. So this is just kind of here to stop that as much. And it just kind of keeps constant power to it so that you don't have like a power surge during a bump or something that will disconnect you from the robot. Once you do build things on top of the robot, though, you'll see a lot more of these pieces. How to attach wires to the battery. Okay, these little clips here, these pink and red clips, you can buy them pretty easily. I don't actually remember what they're called right now. It's just kind of, it's on the tip of my tongue. I can't really reach it. But it's you just crimp them to the ends of the wire. On the other end of the wire, there's just like this metal loop. You kind of squeeze onto the thing. I think so, yeah. But you just kind of screw that onto the battery. You can have these on either end and you just plug them into each other. They clip in, they stay very tight, and they'll stick together. And coming into the power distribution module, you can see kind of these clips here. So you just flick that upright, it'll kind of open the gate. When you shove the wire in there, make sure it's in all the way, enough is stripped, clip it down, give it a couple tugs. And when you power on the battery, as long as everything's plugged in right, it should power on pretty okay. And like I said, everything's color coded. It's very easy to tell where is where. So if you're just looking at kind of the nest of wires in here, you can see that most things follow a pattern of what they're plugged into and what colors they are. But making sure that these are connected is fairly simple because one of these things you do once and it'll stay there for a long time unless you're too rough with it or something. So we had a problem with picking up a battery from the wires, and those clips will come off. But they're fairly easy to put on, and when they're put on the right way, they stay there forever. They're really good. What is the black part next to the radio and what's it for? This piece here? We had problems last year with connection to the radio. So when you got a good bump, shove, push, the power would surge and you'd lose connection to the robot. And then the robot would just kind of be a shell out there. You wouldn't be connected to it. And what it does is it kind of takes the power from the RoboRio the connection from the RoboRio to the computer and just kind of protects it from those power surges or from any disconnections, and kind of makes the radio a bit more reliable. So we don't have disconnection while you're on the field. How does the power distribution differ from the old one? This one here is just kind of more swerve based. So if you look at the bottom here, it's got a lot more plugins. It's got wires you can plug computers directly into this for. It's got some smaller sections as well as big wires, different gauges of wire. They do take newer fuses, which is kind of hit and miss. The fuse is a fuse, but just the way they're constructed is a bit different. It's you wouldn't know it if you just look at it, but there is a difference. It does have a power voltage meter here that shows how charged the battery is. And on the older one, it is very, very bare bones. So looking at the bottom here, it's got the CAN wires. It's got some very boxy, very, very old fuses. And it's got some different connectors here. So you see it's not a switch. They're a little bit less accessible. You've actually got to put like a screwdriver in here to lift the gate up itself. Whereas this one here is very easy. You just flick a switch and it's pretty much done. The black part that prevents the disconnection. This is called the radio power module. Yeah, this is brand new. I haven't really looked into this yet. I can't give you like perfect information because I've only seen it a couple times. Like I said, a lot of the parts on this are very new, and I haven't gotten very familiar with them yet. I kind of know the bare bones, the basics, and kind of what parts are on it. So like this gyro, I helped make a part, connect it to the computer, tell it what's what, but I never really took a deep dive into it. I kind of got it working and sent it off to our coders. Yeah, this is a swerve drive. So it's pretty easy to find on the internet again. But it's almost revolutionary. So like during our competition last year, there were tons of these robots, specifically swerve drive robots, in the competition. And it became very apparent very quickly that you would not do well if you didn't have swerve drive. They dominated. So we kind of went out here with the goal of making one that kind of combated the problems that other teams were having. So we went and visited other teams, saw their versions, saw what you can just buy online, found the weak points, and built a totally new one that kind of defeats all of those problems. And as you can see, it is chain driven on the top here, just regular old bike chain, which makes it very accessible. We've got all these parts that can just move very easy and it's out very quickly. And it becomes a lot more reliable than, say, gears or belts that are grinding together or kind of melting off of each other. The old PDP had too many fuses on the end that would break the circuit for the entire unit. Are they similar to the fuses on the new PDP? Yeah, so these kind of just say if something, say, probably the most common one, these wires are backwards, that you don't just kill this thing because they cost a good chunk of change. And once you break it, you're very upset about it because you don't want to go and drop a couple $100 on a new one. Looking at this one though, it's kind of hard to find those fuses. There is a slot for one right there. I'm pretty sure that's for these wires though. You can see 3 in there. But there is probably kind of a fail-safe built inside of this. So if something were to go wrong, you could disassemble it and kind of fix it. Yes, we did build this swerve drive from scratch. You can go online. You can actually buy the modules. Um, but it's a little boring, right? We wanted to make something that was different than what everybody else had in the way that it was more reliable and a lot easier to work with than other ones. So when you go online, you can buy one module for about $1,000. Most of them are gear driven, which is just gears on gears. And a problem that a lot of teams were having with it is after a weekend, you would run through the gears so quickly, and the teeth would just be ground down to nearly nothing. And the teams with belt had that less often, but they did have belts wearing down very quickly and breaking over time. We kind of asked the question, well, like, why don't people use chain? Or why don't we see it? Everyone kind of had the same answer. A few teams had already done it, but nobody could really figure out how to do it reliably or in a way that's easy to work with. So we went in with kind of two goals, two main goals. To get it working with chain, so it was a lot more reliable than the gear and belt driven ones. To make it very modular. So the ones that you buy online, it's like 22 bolts to get it out of the robot. You actually have to disassemble the frame to get it out. These ones we've built here, if you look close, they have 4 bolts right here. And these 4 bolts just come out. The whole piece comes out in one go. Again, this isn't kind of a finished product. These two motor controllers will actually be mounted underneath here. So we can take it out, plug in 2 wires, and have a new one in there faster than we can fix this one itself. But yeah, these are still prototype ones. You can see they're not finished with anything. It's just raw metal, all that kind of stuff. But over time, we've been editing, we've been finding the problems, and we do have a design for a version that we want to kind of complete it with right now. But at the moment, it's kind of hard to find the materials. Um, but yeah, all these pieces here were
Oh,
seen
one is yours, right? Yeah.
by one of our mentors uh, that we have on our team. Owns a shop with a CNC machine, so we designed all these parts and had them custom milled to the way that we wanted them. Setting a Canva system. Um, Canva systems are not really my forte. I kind of send that to the coders. I kind of just plug it in. But I know kind of the basics about it. It's just taking information and feeding it kind of like a conveyor belt, where it's like putting everything on one conveyor belt, and different parts of the robot will pick off the pieces that relate to them. Another way to think of it, the way it was explained to me, was it's like a bus where it has multiple stops. So it takes in all this information. It will go to a stop, and it will look at the bus and say, these parts are mine. Take those, and the rest of the parts keep going around the circuit to the next stops until they find their designated like place to be. Um, but yeah, usually I just kind of plug in the bare bones. I give it to my coders because they know a lot more about it than I do. If you get to know me more, my code is pretty bad. I'm a lot more hands on than I am looking at a computer, which is another part of FRC that I really enjoy. So if you're not good at selling, if you don't enjoy something, it's very easy to find a part that you do enjoy. So I went in with kind of the knowledge that I'm not a great coder. I'm not good at sitting at a computer, looking at something and understanding it. And we always find ways around that. So I kind of lean more towards the actual mechanical part of the robot, and I've been here for as long as I've been on the team. Do we have any other questions for people? Comment on the components of a pneumatic system. Okay. Pneumatics are pretty simple. We use them on the goalie robot to control the limbs. It's basically just a big piston, like a big cylinder. There's a input on the top and an input on the bottom. When you put air in one side, it'll kind of push that plunger towards the front using the air pressure and extend that arm that is inside that rod. And when you put air in the other way, it forces the air that's already in there out the same way it came in and creates air pressure on the opposite side, kind of retracting that rod. To control it, it's we had it connected to a button where different buttons corresponded to different pistons. And it's connected in a way where you take this module here, the pneumatics hub, you connect a power and a ground to the actual button, and then you're kind of telling it when there is an input, send air one way. When there is another input, send the air a different way. When you're finished building the Swerve drive and get it perfected, would you be sharing your design and how to build it? Yeah, very likely. We don't really take this as something that we like want to trademark and keep to ourselves because it's ours and we did this. It's another whole part of FRST. If you go to a competition and you need something, you can go to another team and say, "Do you have this?" And they'll give it to you without question. FRST isn't a real, though it is a competition, it's not very competitive per se. It's more everybody is here to have a good time, even though you're competing against each other. So, though you are going up against each other and you are going in there with the goal of being better, if somebody has a problem, if somebody needs help, everybody from all over the place kind of just shows up. For instance, we had a broken part on our claw last year, and we had the whole build like team of another team just show up and start helping without saying anything. And I haven't really seen them since. They just kind of showed up, helped us get back out there, and just everybody's very very helpful, very inclusive, and they're always there to help you finish something, even if it isn't. But yeah, when the Swerve drive is perfected and it's really done, and we know it's working, if people want the design, if they think that it's something they could build, they could figure out, then usually we'd be pretty happy to give it to them. We're not all about keeping everything going well for us to ourselves. We want everybody to enjoy what's being discovered. Neo motor versus Kraken motor. The Neo motor is the one that we use in these robots. Most of ours are brushless, which is it's I'm pretty sure electromagnets. They move very quickly compared to motors that have actual contact. A Kraken motor, I've heard about them. I've seen maybe one. We don't use them very often, so I don't have a lot of knowledge on them just because I haven't worked with them. But as far as I know, they're pretty similar to the Neo motors. Most motors are kind of the same thing. There's a power and a ground. You plug them into a motor controller and they do what they tell you. Sure, different motor brands could be useful for different uses, different things you want them to do, stuff like that. But for me, no, I haven't really worked on them that much, so I can't give you that great of knowledge. Techniques for troubleshooting if the robot control system's not working. Usually it's a code thing. Sometimes it's a wire thing. It's always hard to find. The first thing that I'll usually do is if something's not working, I'll get them to uh, put an input in. And if it's doing something random or not doing something, I'll just unplug a part, get them to give it the same input. If it does the same thing, then that wasn't the part that's doing something wrong. Put it back, pull another part, pull another wire, whatever, another connection. When I pull a connection that makes the robot do something different, I know that that specific part is where the problem is. So I check the wires right away. I make sure that everything's plugged in the right spot. And if so, I take that part in question to my coders, to the coders on the team. I tell them this part is acting up. Here's what it's doing when I give it this input. It should be doing this instead with this input. And they go in there, they edit some parts, and we just guess and check really. Uh, I'm sure most of you will know putting in code, writing code, whatever, it never works on the first try. You've got to give it a lot of trial and error until you get to where you want to be. As soon as we get there, we save the code. We make sure we don't make a mistake that puts us in the same position that we were in. But yeah, usually I just start pulling wires when the robot stops doing what it's doing. That's the part in question. I work on it and I take that to my coders and they'll look through it and see if they find any bugs in the code. Because sometimes they can be pretty hard to pick out of a huge paragraph of writing. Um, any stories you may tell of lessons learned? Um, yeah, actually, pretty recently. We keep our competition robots after the fact for a little while. We'll go to elementary schools. We'll take them to community events and just show off kind of what we're doing. So we're always interested in giving back to the community that's helping us get to the places we are. So we get a lot of small town community sponsors, a lot of people helping us without any real profit, any real take back. They just do it because they like it or they want us to be successful. One of our robots just totally went haywire. So the controllers, we have the actual, it's almost like a PlayStation controller that's for actually moving it. We have what we call a co-pilot, which is a box with all kinds of buttons on top of it. And that will control everything that isn't it moving. For some reason, those swapped places. So moving inputs on the PlayStation controller was like doing random stuff to the robot based on like the claw, the arm, whatever. When you pressed buttons, it would start moving. And one of the buttons in particular would make it spin in a circle at top speed and it would not stop. And we were pretty lucky to find out when we did, we had it on a stand. But if we had it on the ground, it would have been pretty horrible because they go fast. If you look at them, they go very quick. And spinning one in a circle, it's prone to tip over, it's prone to run into things. We were pretty lucky to figure it out there. But it took a couple days of fishing through the code to find some very, very tiny problems. Um, it just shows how specific these robots are. If you take a one and change it to a three, it's going to do something totally different. And kind of the learning curve that everybody gave me, but that was it's only going to do things wrong if you tell it to do them wrong. It's only going to do what it's told. If it's not working the way you wrote it to work, then it's your fault, not its fault. You're always going to be the person that's making it doing what it's doing. It's it's there is times where it's going to do things randomly. Sometimes it's not your fault. most of the times it's usually you that did something wrong, whether that was just a kind of rushing mistake or something you didn't know. But either way, it's always something where you can kind of pick it apart and find the problem. You have a lot of people working on the same thing. It fixes it pretty quick. And again, working around people that have more knowledge than you or are learning with you is really helpful for getting a grasp on on new things that you haven't learned yet. We've also had problems in the past where robots do decide to do things for no reason, and that's always interesting. It's always a bit scary because when there's big things on top, they'll just kind of run around. Um, we had a robot that broke a radiator at our school because it went haywire and hit the radiator and it just like fell off the wall. Um, but stuff usually happens because you're telling it to do that, not because it just decided all of a sudden it wants to do this. How do you onboard new students and mentors so they may become more familiar with the control system? Usually, we'll turn down the robot's speed very very low, so we'll keep it around 20% maybe. We'll take all new people that are interested in driving them, controlling them, whatever, and give them a chance to just kind of get a feel for it, right? And if they're enjoying it, they can stick around. But ultimately, getting closer to competitions, the people that are going to drive in competition are the people that have the most hours driving, the most experience with this robot in particular. So last year we drove very intensely for I think it was 4 weeks. And the people that were driving the most or got the best at it fastest were the people that were driving it. But that's not necessarily how it's going to work. It could just be whoever's interested in it. It could just be whoever decided communally should be doing it. For us, though, it's hour based. People that drive write down the times that they drove from. It's tallied up at the end of the month or whatever. Whoever gets the most hours is the person that knows the robot the best. So they'll be the one out there. Any other questions? Doesn't have to be like electronics related. It could just be related to first. Okay. What's your design strategy after kickoff? Um, right after it's released, we'll all stay for a couple hours and we just pepper ideas at everybody. So we'll usually have our lead mentor in the middle, just with a computer writing down stuff. And you'll just put up your hand with an idea and they'll just pick off. We make a huge list of all these ideas we have. And as we're building, we kind of pick out the best of all of them and build something that has little bits and pieces. So say somebody has an idea for a claw, somebody thinks they could do it better with another piece, someone else thinks we should do it totally different. We kind of, instead of picking one of those and going off it, take a piece from each of it, the piece that is the most foolproof, that works the best. And we kind of incorporate them all together. So it's not like your ideas are invalid if they're worse than someone else's. It's everybody has ideas that are always helpful. And even if your idea isn't the final one being used, pieces of it, thoughts from it, or even the ideas that you spark, just bringing that up is always useful. So you shouldn't be disappointed if a piece or a part you think about isn't used because it's influenced something bigger. But yeah, it's usually just us peppering ideas at each other and deciding what's good based on the event that we have that year. Dedicated person or group responsible for the electrical and working. Um, it's kind of preference for the team that you're working with. So for my team, we call executives, where it's people with the most knowledge in that area will kind of lead all the other people when working on that area. So they're not necessarily making all the decisions, but they're making sure everybody has a job that they can enjoy and they can excel at. So for instance, myself, I'm the lead builder on our team, so I kind of look over everything that's physical, mechanical. I don't really look at computers that much. I'm a lot more nuts and bolts than I am real programming. I do take care of the wires because that's kind of part of my job. Most of my job isn't actually doing things. It's making sure other people have things to do, which is just helpful for our mentors. It's just they can be focusing on something else and not have to worry about all the people around them. Um, Another big part of my job, not as much building it, but knowing what it does. I need to be able to go to a competition and they come back and say, this piece isn't working. And I know all the places to check to figure out why not. Um, so I need to be able to look at something and understand all the bits and pieces of it to say, this is broken, fix it quickly. That's usually how it works. So you don't get much time to repair your robot during a competition. It's usually like you have 30 minutes. It's not working right now. Make it work. Um, but again, there's always people coming in and helping you. It's just knowing where to check when things have gone wrong is is just important for when you're on a time crunch. Um, Personally though, I do recommend having people dedicated to the different sections of the robot. I find it a lot more organized instead of everybody going to one main person, the lead mentor or whatever, with all kinds of problems, ideas, all that. It kind of divvies up the workload. So all these different people have different dedications, and it's also very helpful for like it's really helpful for when you're actually doing something because you're taking people that have or what they're best at essentially and giving them most of the work that comes with that. So it usually goes a bit quicker and it takes a lot of the workload off of other people so they can focus on something important and very specific instead of kind of jumping back and forth between different parts. But yeah, we have all kinds of people. So we've got coders, builders, we have media people, newsletter people, people that like talk to important people. Um, Even if you're really not, if you're better at talking with people than you are at working with people, there is jobs that require you to just talk to people. So there are jobs that it's just you going to other teams, talking to them, asking them what they did differently, why they thought that way, what they think they're good at, what they think they're bad at. It's just there's a lot of scouting involved as well as actually doing things. So we have parts of our team called the scouts that will actually just research the teams that will be going to competition with us and finding what their resources are, knowing what they're good at, and knowing what we'll have to compete with. We can kind of build to combat that before they even know we knew what they did. because most teams do have media. They'll put pictures online. They'll put newsletters up. They'll update the people that that want or need to know. And if you can find that, then you have an upper hand on them because you've basically taken their whole plan. And as much as you can pick it apart and take some ideas, you're also building in a way that's going to combat that common competition. So it's building around their ideas or with them. But no, even if you think you don't have any skill that could be useful to a robotics team, everybody's got something that has a use that's very important in the bigger picture than it is in that moment. So all these little parts and pieces add up into one great thing that's just it's something to look at and be proud of.
So, dear Sam, we're most appreciative of the insight you brought to the FRC Robotics Control System this evening. A lot of enthusiasm and experience are clear in your presentation, and really appreciated the little anecdotes and of course, the TSN goalie robot, all the rage out there. It was quite popular in the world of FIRST when it was released. And yeah, just most inspiring what your team has done. The drive module shown in the picture right there may represent a turning point in the world of swerve, literally and figuratively, as they may make swerve accessible to more teams than is currently the case. And just all around an inspiring team in 7200 Banting Memorial, and a great group of peers you had there at the Georgian event. And we really look forward to seeing you in the events this year. I'm sure if anyone in the group here has more questions, we could pass them on to Sam and the team at 7200. And yeah, once again, thank you from everyone and on behalf of the whole FIRST community here in Ontario.